Hello. I thought in this video that we should talk about finding the area under a curve. Now we know how to take an area inside a square or a rectangle, base times height, or even a circle, right? Pi r squared, or an ellipse, pi ab. We're not going to go into those right now, but there are some obvious ways to take areas. But how do we take an area under some f of x? Some y is equal to f of x function here. Well, it's not quite obvious at first, but what if we just try to get close to it? I mean, we could put, like, let's say we know about circles, so what if we put, like, a bunch of circles in here? These aren't actually well-drawn circles. What if we put a whole bunch of circles in here and just ignored the gaps in between? Right? That would work. But that's not really solid. That there are so many gaps and it doesn't really, there's no really strict way to do it. So, we could try some of our other ones. There are other ones that would be just like that, though. Like we could do ellipses, or let's say triangles. Triangles might be a little better, because let's say made a triangle here, and then like a triangle there, and like a triangle there, and so on. But it's not really great, because then it gets really hard to do, and they're not perfect. And it's never going to be perfect, but it's still not really mathematically defined. So, that leaves us the rectangles and the squares, at least for our purposes. And I lost a little bit of x-axis here. So, what if we made squares, or rectangles? Well, rectangles would seem better for this graph. We could do a rectangle here, and that's, it's not perfectly lined up with the graph. It's just kind of close. And then we could do, let's say, another rectangle up here. And it wouldn't be perfectly aligned. See, there's some extra space there. And then a rectangle up there. And then a rectangle up here. And then a rectangle up here. And then we keep doing that, and look, there's all this space in between, but maybe there's a way to get rid of these spaces. What if we made, I'll erase this a little bit. What if we made our rectangles slimmer? What if we made them even slimmer so that they fit almost even closer with the graph, and that those little gaps are much smaller, so we get the area a lot closer, right? We could get the area really close, or we can make them even smaller, depending on how accurate we want it to be. But how do we mathematically define this sum? Well, we could call the width of a single rectangle, I'm going to write it down here. We could call the width a little change in x, right? Right? We have a tiny little increment of x, like let's say 1, or 1/2, or 1/4, or 1/64, or whatever. And then our height is, as always, f of x, right? This height here is f of x, right? That's what our function is. This is f of x. Alright, so I guess we could just multiply base times height, delta x times f of x, and then sum them all up, right? And we have a way to sum things. It's called sigma notation. So we could sum up all of the heights times the little depths, right? And what's our little depth equal to? Well, let's say we want to find the area from one place to another. Let's say A to B. So, this space would be, let's say, A minus B. In this case, B could be 0, so it's just A. But we'll write A minus B for this distance here. And then we could just divide by the number of columns we want, right? The number of our little rectangles. Alright, and the sum be the sum of all of these from x values that are equal to, from, let's say, our starting point, B to A. And we could find just the sum, depending on how accurate we want this to be. We define our bounds, where we want to find the area from, and the number we want, and we find a small value, and then we can, this is just some constant. And then we sum up all of those areas from our selected values. Alright, now this is something called a Riemann sum, and it's basically trying to, as I've been doing, find the area under a graph. In the next video, we'll explore how this results to calculus and differential calculus.